Someone is praying for you. Someone is praying for you. So when it seems you're all alone and your heart will break in two.
Hello, welcome to our lessons on application of ordinary differential equations as first order, of course. In this lesson, we are taking a look at another nonlinear model, and we are looking at chemical reaction, and we'll be taking a look at the law of mass action. Chemistry is actually a branch of science which is concerned with the substance of which matter is composed, the investigation of their properties and reactions, and the use of such reactions to form new substance. And mathematical models are used in chemistry to solve problems of chemical nature. So we want to begin with the law of mass action. And the law of mass action says that the rate of chemical reaction is proportional to the product of the concentrations of the reactants. So the rate at which the reaction takes place is proportional to the product of the concentrations of the individual reactants. And two aspects are involved in this initial formulation of the law. The first one is that the equilibrium aspect concerning the composition of the reaction mixture at equilibrium. The second one has to do with the kinetic aspect concerning the rate of equation for elementary reactions. That is the rate at which the reaction takes place. Now let's look at how we can formulate the reaction model. We want to take a look at biomolecular reaction, which is a substance consists of the reaction consists of two substances, say A and B, which suppose that 1 mole of A combines with 1 mole of B to form 1 mole of C. And the chemical reaction is written in this nature. So we just have the 1 mole of A combined with 1 mole of B to form just 1 mole of C. That's what the case we want to take a look at. Now, since a mole of A combines with a mole of B to form a mole of C, the number of molecules of A present at any time t is A minus C. Because we are saying that what we are doing here is that we are letting the number of moles of A, we let the number of moles of A be equal to small a, that of B equal to small b, and that of the chemical C, that's the product, equals to small c. So at any time, the number of molecules of A present at any time is simply A minus C. That is, we subtract the number of molecules of C formed from A, and that of B is B minus C. So this gives us the concentrations of A and B at any time during the reaction. And using the law of mass action, we are saying that the rate of chemical reaction, so we are looking at the rate of change of concentration of C. So we are saying that the C dt is proportional to the product of the concentrations. So we know the concentrations are A minus C times B minus C. So when you introduce the constant of proportionality, you're going to have the C dt to be equal to K into A minus C times B minus C. And at the onset, the initial concentration, we know the concentration of C at the initial time is always 0. So this gives us the IVP that we are supposed to solve. This equation is separable because A and B are all constant. They are the initial concentrations of substance A and substance B. So we can separate the variables. So we can say that this is the C over A minus C, and then B minus C equal to K dt. And before we can integrate this, we need to resolve this into partial fractions. So I want to do a very shortcut way of dealing with the partial fractions. So a certain letter M is multiplying A minus C plus a certain letter N is multiplying B minus C equal to 1. Now since M is multiplying A minus C, it means M is being divided by B minus C. And since N is multiplying B minus C, it means N is being divided by A minus C. So that is the technique. This is just a digression to simply give you the shortest form of getting this. When C is equal to A, this M will be 0. So you're going to get N to be 1 over B minus A. That is, you are going to have B minus A here. And when C is equal to B, this is going to give you a 0. So you're going to get M to be equal to 1 over A minus B. Now I want to write this one as negative 1 over A minus B. So let's continue with a digression here. So that means that we can factor 1 over A minus B out. Don't forget that I said N divides this and M divides this, and now N is negative here and is dividing this. So this is going to be negative and this is going to be positive. So you're going to have 1 over B minus C minus 1 over A minus C dc equals to K dt. So 1 over A minus B is constant, so we want to send it here and integrate both sides. So we're going to have the integral of 1 over B minus C minus 1 over A minus C dc equal to A minus B, the integral of K dt. So this is going to give us a ln of A minus C over B minus C equal to A minus B kt plus, let's say, ln D. So when you put them together, you're going to get a ln to be equal to A minus C over B minus C multiplied by D equal to A minus B multiplied by kt. So having this, you can take away the ln of both sides. You can take the exponential function of both sides, and you're going to get A minus C over B minus C e raised to power D times e raised to power A minus B kt. So now we use the initial condition C of 0 equal to 0. And here C is 0, so you're going to be left with A over B. And since T is 0, everything will go 0, and this will become 1, so equals to D. So now the equation now becomes A minus C over B minus C equals to A over B e raised to power A minus B kt. So we have it this way. We're making C the subject. You're going to get C of T to be equal to AB into bracket 1 minus e raised to power B minus A kt all over A minus B e raised to power B minus A kt. But don't forget, I only interchange this. When I interchange, this is negative of this, so I just use it to be a certain rearrangement here. Now we are saying that from this equation, if B is less than A, then the limit as t approaches infinity of C of t is going to be AB times 1 over A, which is going to give us B. And this means that the reaction must stop when all B has been used. Example 1, when chemicals A and B react, one molecule of A combines with one molecule of B to form one molecule of C. Suppose that at the outset, the concentration of A is 2 moles per liter, that of B is 3 moles per liter, and that of C is 0. After 1 second, the concentration of C is 0.2 mole per liter. Find the formula for the concentration C of T of the substance C after T seconds. Find the concentration of C after 3 seconds. What is the concentration of C after the reaction is complete? So this is the question we want to solve. So let's look at the information here. The information here are the number of moles concentration of A is this, that of B, and initially that of C is this. Then after 1 second, we have that of C to be 0.2. So these are the information that we need from this question. At time T equal to 0, we are talking about initially. Concentration of A was 2, that of B was 3, and that of the substance C is 0 because nothing had been formed. Then at any time T, concentration of A now becomes 2 minus C, that of B now becomes 3 minus C. So these are the concentrations of the reactants A and B during the reaction. So from the law of chemical reaction, the law of mass action, we are saying that the rate of change of the concentration is equal to K times 2 minus C times 3 minus C, with C of 0 being equal to 0 and C of 1 being equal to 0.2. So this is the model. This is the model for the problem, and we need to solve this IVP, and it's separable. So we are going to say that the C over 2 minus C 3 minus C equal to K dt. And we know we might resolve this into partial fractions. So if we resolve into partial fractions, you are going to get 1 over 2 minus C minus 1 over 3 minus C. The C equals to K dt. So now we integrate both sides, and this is going to give us ln of 3 minus C over 2 minus C equal to KT plus e raised to power, or ln of D, plus ln of D. So when you put them together, we are going to get 3 minus C over 2 minus C equals to D e raised to power KT. I will bring the D here to come and join. You take the exponential function on both sides. Now we know C of 0 is equal to 0. So when you put them here, you are going to get 3 over 2 equal to D. So we cannot write this whole thing as, don't forget, in all these cases you are solving for A. Cannot write all this thing as 3 minus C over 2 minus C equal to, so 3 minus C over 2 minus C equal to give us 3 over 2 e raised to power KT. And we have a second condition, which is C of 1 equal to 0.2. So that will give you, when you put them in here, we are going to get 3 minus 0.2, which will be 2.8, over 2 minus 0.2 will be 1.8, equals to 3 over 2 e raised to power K. So if you make e raised to power K the subject, you are going to get 28 divided by 27. That is e raised to power K. We don't need to find K because I have e raised to power K here. So this implies the e raised to power K all raised to the power T is now 28 over 27 to the power T. is a power. So therefore we are going to have 3 minus c over 2 minus c equal to 3 over 2 times 28 over 27 raised to the power t. And when you make c the subject, you are going to get 6 times 28 over 27 raised to the power t minus 1. The whole thing over 3 times 28 over 27 power t minus 2. So that solves the first part A. The B was asking you to find the concentration at time t equals 3. So at the B, t equals 3. We are looking for C of 3, and that when you compute them in, you are going to get 0.514 mole per dm cube. Then the C is asking us to find the concentration of the substance after a long time. That's the limit. So first and foremost, what you do is that with this 6 multiplied by 28 over 27 to the power t minus 1, all divided by 3 into 28 over 27 t raised to the power t minus 2. Now, to get the limit as t approaches infinity, we divide each term by this one. So we are going to have c of t to equal to 6, 1 minus 1 over 28 over 27t raised to the power t, the whole thing divided by 3 minus 2 times 28, that's divided by 28 over 27 t. So quickly we can obtain this one as the limit. When you now look at the limit of c of t as t approaches infinity, you are going to get 6 over 3, which is 2.